So welcome to the part 7 of the Algebraic Structure course, an online course that I am delivering. And the textbook that we have adopted for this course is Abstract Algebra, Theory and Applications by Thomas Judson, which is available free of cost. You can just Google it and download it. Okay. So remember that we call a non-empty set G a group if it has a binary operation, such that if we combine A and B via AOB, that is also in G, is called closure property. And for any set of 3 elements, we can pair them any way around. If we are taking their product, this is called associativity. And we have identity in here such that EOA is A for every A, and actually we saw that this also holds true if this holds true. And for each A, we have an inverse such that A inverse OA is E, rather the inverse of A, and we saw that A multiplied with A inverse is E as well. Okay, so now let's just get used to some terminologies and some symbols. So you saw that set of real numbers is a group with respect to addition. So here identity is 0, and for any A inverse is what? Negative A, right? Because A plus negative A is 0, right? So this looks slightly like anomalous, but we just have to get used to it, because here our binary operation is this. Oh, and very soon we shall even start dropping this operation while discussing material. Okay, and here what happens is that, say we took R star, where R star is the set of non-zero real numbers. Okay, so R star is R minus 0. Okay, then that is a group. Identity is 1, and for every A we have a reciprocal of A, and here it's matching with the terminology, right? Excuse me, here. So O is this multiplication of numbers. So what we have to get used to, as I said, is this. Say for example, if I say A square here, that is AOA, that is A plus A, and that is 2A. So when we are talking about this as a group, okay, with addition as the binary operation, A square is 2A. Don't worry, we will not get too mixed up in these, but just letting you know. But here A square is the same as usual, AOA, the way you are used to. Okay, and then you also had situations in which this O may be commutative or not commutative, right? Okay, so in both these cases, multiplication of real numbers and addition of real numbers, they are commutative, right? So I'm starting with a new slate now and recalling the same group, additive group of real numbers. And again, if plus is our binary operation, then that means A square is AOA equals A plus A, that is 2A. And then just something slightly different. Say I have AOB square, and here A and B, they are real numbers. Okay, we should write that down. So what that means this is A plus B, and that will become what? A plus B plus A plus B, right? And again, we should just say this, that is the binary operation is plus here, just to remind us ourselves that we are in the we are doing this for a different operation because of this. So keep that in mind again. And then this part here becomes a square. This guy here is O, and this thing here will become B square, right? And of course, if you have this R star with respect to multiplication, excuse me, this process follows along, much more easily. Let me just change the letters here. So say we got U, and I'm not writing O here, and so this would be U square times V square, and because this is very easy to see this as O. And now, as I mentioned just a few seconds ago, that both these operations are commutative. So what happens here is that whenever, see here, we were able to interchange the places of A and B. So this kind of a relationship, that AOB square equals A square OB square, was, that just became possible easily. But let's look at the groups in which we have the binary operation not associative. And let me do this here. I'm looking back here and feeling awkward. That is, it looks like a weird sentence. Now I think it's a little clearer. Okay, so let me recall another group for you, which is not commutative, that we constructed, I think, a couple of presentations ago. Now let's take this group of quaternions, which is a non-commutative group, as you can see right here, right? That the operation is not commutative. And instead of calling it Q, because Q is reserved for the rational numbers, we are calling it H in the honor of Hamilton, as who is credited with the discovery. And what is our curiosity here? We just saw that in an abelian group, we had this property, right? Okay, just like power property that you have been used to. So we want to know if this is true in general. And if you recall, when we were working with A plus B, right? Okay, so we could write this as AOB. Then again, AOB, I could just remove the brackets because of the associative property, right? And then let's look at the middle, because that's what we needed to switch, right? So this will become AOA, then here BOB, right? So what happens then is, that is, this is what we got, and then we have this, and we got this. And you can see that I am just being distracted in my mind while writing. Here I'm assuming that these are commutative. See this here? Or if that is given, then they will be commutative. So you may notice this here. I can left cancel A and right cancel B. So in case this happens, then you can, on the other side, you can write it as a neat argument, arrive at a conclusion that BOA is AOB. So that means if this happens for all the pair of elements, then the group will be commutative. and this group is not commutative. So let's try to find something for which this is not true. Okay, so I'll give you a separate exercise to extract just a little neat proof from my mumbling that I just did. Okay, that in case this is true, group will be abelian. All right, so now just do this. Let's just go to the original question because I got distracted. But anyways, we shall do an exercise based on this. Okay, all right, good. So here, let's do this. Let's take A to be simply I. All right, and let's take B to be, say, J. All right, and see what happens. AOB square is going to be IOJ is square, okay, and that is going to be K square, and that is going to be -1, right? And if we write A square OB square, then that's going to be I square, then combined with J square, and that will become what? -1 times -1. Now that is +1 in here because everything else followed just the usual multiplication law. So we could see that in here AOB square is not equal to this. So that means this equation, or rather this equation, is not always true for a non-commutative group. Okay, and so that's a property that holds for all the elements only for commutative or abelian groups. Okay, so and with the discussion that we just did, and here I have typed it all like clearly, we can show that, okay, if G is a group, then in case this holds for a pair of elements, then those pair of elements commute. All right, and let's just make not get that informal. We would be, let's indicate here, okay, rather in a different way. That is, let's show that for AB in G, okay, in case this equation is true, that means this pair of elements commute. And you know this, that if these commute, you can just write it out and see that this equation is true. So you can change this to if and only if you would like, okay? Now, let us proceed further with our discussion. I mean, this is only a one-person discussion. I hope we had a group in which we were discussing it. But anyways, so you saw this. We began with, say, the set of natural numbers, and this is not a group. Okay, all right. Whether it's plus, for plus, it is not a group. One simple reason, it doesn't have a zero. For multiplication, it is not a group, sorry, because it doesn't have all the reciprocals of the numbers that we have. And if we go to the set of integers, then this is a group with respect to plus because, of course, plus is associative, zero is identity, and if a is an integer, negative a is an integer, okay? All right, so with respect to plus, it is a group, but if we if you recall, it's not a group with respect to multiplication, because first of all, even if we take the non-zero elements, because the reciprocals are not in there, right? So, and then I'll just recall just two more examples and then extend it. So we saw that this set of rational numbers is a group with respect to addition and not with respect to multiplication, because zero created a problem there because of non-availability of the inverse. But if we remove zero, then it is a group with respect to multiplication as well. All right. But what do you have here? You have Z is a subset of this Q, right? And at the same time, Q is a subset of R, okay? And also, R is a subset of C, right? So integers are contained in rationals, they're contained in reals, and reals are contained in complex numbers. And all of these are groups with respect to the addition. So what we say here is this, that Z with respect to addition, we can call it a subgroup of the set of rational numbers. Also, it's contained in the real, so it's a subgroup of set of real numbers. So we may say this is a subgroup of the group of rational numbers, right? And at the same time, sorry about that. So at the same time, we can see that it is a subgroup of the set of real numbers as well, right? So if we want, we can just take R here and realize that this is a subgroup of real numbers as well. So what this will do is that this is going to just reduce the burden of proof of these statements for us once we start refining a statement, that instead of proving that this is a group in, completely in its own right, and then showing that this is a group. Okay, so in case this subset is contained in a bigger set, which is already a group, okay, it should inherit some properties which should make it meet rather fewer requirements. And I'm running out of English, so let me just go to simple statements. So let's take a finite group. For instance, let's take the group of integers modulo 4, where, remember this, we denoted them how? We denoted them by these symbols. Let me just write it and bring it back. So these are the integers modulo 4, and this is the addition modulo 4, and this is a group. And in this, the how the addition was defined, if you recall, if we add, say, 1 with 2, we simply get a 3. We will leave that at 3 because 3 is smaller than that, right? And on the other hand, uh, if we have this, say we wrote 3 plus 3, that becomes class of 6. And the way we bring it in here is this, that is, we just divide 6 by 4, and that becomes the remainder is positive remainder is 2. So we just make it a 2, right? Okay, so and soon we shall be like dropping all these formalities here, that is writing subscript here and writing these bars, but let's not worry about it. So Z4 is a group, right? And let's take, say, a subset right here. Say we took the subset, sorry about that, 0, 2. Then you can check that this is a subgroup of Z4, okay, because you can see that first of all, we are taking associativity as inherited, right? And closure has to be checked. So let's check it verbally. 0 plus 0 is 0, 2 plus 0 is 2, and 2 plus 2 is how much? 4, and that is a 0 because divide 4 by 4, the non-negative remainder is 0, right? Okay, so that is a subgroup. On the other hand, if we took this, say we replace 2 by, for instance, say 3, okay, then we will say, then you can see this is not a subgroup, and the reason being simple, that we just saw 3 plus 3 is 2, so this operation is not a, one moment, I have to give it a different name. So it's not closed with respect to the operation, right? So because it is not closed, okay? All right. So, so let's go ahead and look at these examples to see that how do we like trim the requirements or the group requirements of something that is already a subset of a group, okay? So now you saw that if we take Q, the group of rational numbers with respect to addition, Z is a subgroup, right? Because it satisfies all the properties. But N, the set of natural numbers, is not a subgroup because, in the way we are taking the set of natural numbers in our group, sorry, in our book, we are treating only the positive counting numerals as natural numbers. So this is not a subgroup because, of course, neither it has 0, the identity, okay, nor does it have the inverses. On the other hand, let's recall that Q star, the non-zero set of rationals, it is a group, but Z star, say we take non-zero integers, okay, it is not a subgroup. And here you could see that N was closed with respect to addition. It is still, it was not a subgroup, right? Now here Z star is, I think it's going to be closed with respect to multiplication. Two non-zero integers will multiply to non-zero integer. It has the multiplicative identity. Remember, 1 is the identity for multiplication, but it fails to have what? Inverse property, right? Other than the numbers 1 and -1, nobody else has the inverse for multiplication in Z star. So that failed to become a group. And likewise, say we go to our example, remember that Z4 or integers modulo 4, okay? So if we look at these guys, okay, let me just write them here. We have 0, 1, 2, 3, and our operation was plus modulo 4. And if we did this, if we took only this as a subset, right? I think we call it H. Okay, so this is 0, 2. I hope I didn't pick a wrong color. So we saw that this is a subgroup. It satisfied everything, right? Now let me take like a bolder color here. And on the other hand, if we took this, even though we are just choosing to keep the identity here, okay, but 3 plus 3 was a 2, and that did not live in here. So what happens is this is not a subgroup, right? Okay. So what we are finding is this, that we must need, I mean, here we are failing closure, here we are failing inverse, okay? So if you do this, and I'm going to leave that as an exercise for you. So what we just did is that if I have a group and I have a subset of that group, which satisfies all the properties of being a group, then we call it a subgroup of the bigger group, that is G in this case. Now, what I'm asking you to show is this, that if GO is a group, okay, and so you can show that, and here I'm putting another requirement because of the condition that we put in, that a non-empty subset H is a subgroup, okay, is a subgroup of G. And I'm not going to stress the operation, because if we start with this binary operation, then for groups we'll stick to that for the remainder of the discussion. Okay, so here if and only if there are we just need two conditions. First of all, H is closed. Okay, that H is closed under okay, let's keep writing it just for a short while. Okay, and B is that if H, if A is an element of H, okay, and that's why we had to take that as a non-empty subset, okay, then what has to happen is this, that we must have A inverse in H as well. So you can see associativity, of course, will be inherited, right? And in here, one way is very easy, because it is closed means A times A inverse will be the identity, okay? And because of the closure, it will be in there, so it has the identity in there already. So this part implies that that is a group. All right, so let me let you write the formal arguments as an exercise, and I shall, yeah, let me just prove with you, all right, or rather in this discussion, a very similar property. All right. So what we are doing here is that we are looking at the properties of a subgroup of a group. So this was one property. And now what I am going to try to do is this, that I am going to try to combine these two properties into one statement. So the way that we shall write it is, let's call this one moment, okay, property one, okay. Now let's go to property two, all right, and property two, what we are doing is this simply, that we are combining these two. So here we have similar situation, okay, and then what we have is that I'm changing those two statements to this, that if I have A, B as elements of H, okay, then that should imply that A times B inverse should also be in H, okay? So what will happen is later on, when we are just going to verify that whether a subset is a subgroup, and we can look at that structure as a group, then this will be easier. Okay, so what we have is, you see there are lots of implications here. We are saying if and only if, right? So let's do this. That is, prove one part, that let H be a subgroup of G, right? Okay. So let H, sorry about that, be a subgroup of G, right? Okay. Then what we have to show is that if these guys are in there, okay, then AB inverse is in there as well. So let's go like this here. Okay, that is, we have this implies, since BH is already a subgroup, so B inverse has to live in there, right? So B inverse is in there. And since H is already a subgroup, all right, well, let's write this methodically. What's the hurry? Okay, so that happens because H is a subgroup. Okay, all right, so let's write it down. That is a subgroup. Okay, and this implies that these two are in here because H is a subgroup. So here, subgroup, so it should have inverse. That's why we got B in there, implying B inverse is in there. And this comes from the closure property, because if two elements are in there, then their composition is in there as well, right? Or their product is in there as well. So we have realized this part, all right? So I'll be very happy. It just all looks trivial to you, because all I'm doing is writing it formally, and will expect you to write it formally on your exercises. All right. Now, at this time so we have proved the one direction. Now here what I would do is this: let H be a non-empty empty subset of G. Okay. Now what, and at this, and it does this, that it satisfies, oops, sorry about that. So what I wanted to say was that it satisfies this property. Okay, then we have to show, that H is a subgroup of G, right? So H is a subgroup of G, right? Of G. So we know this, that associativity, or let's write it formally. Sometimes I just speak, not write. This is associative. Okay, and the reason is this, because G is a group, right? And okay, so what we have to show next is that we have closure here, right? So we have to show that if A, B are in there, then A times B has to be in there as well. All right. So remember this, AB is in there, right? So that implies that AOB inverse is in there as well. And let's just go on this, or maybe we can prove it in different order. So I'm just thinking out loud, and instead of thinking out loud in front of the whole world, okay, let me write it concisely. So actually, instead of writing concisely, I meant that think concisely. Okay, so we are going to show it in a different order. So uh, we are not going to show closure first. Let's show that it has identity first, because if it has only one element, that will have to be identity anyways, right? So if A is in H, then we have AA also in H, right? And again, remember this we are getting from our, the bigger one. That is, if A is there and A inverse is there, then AOB inverse is in H. And who is AOA inverse? That's identity. So what we showed was this, that identity lives in H, right? So we have the identity. Now say we have to show this. We showed that AA inverse is in there, but the product is in a set doesn't mean that the factors will be in there as well. So now we have to show that A inverse is in there as well. So what we are going to do is this here. See, E is in here, and we have EA in H. So in this one, what we are going to do is that we are going to take E as A, and for A we will take, sorry, for B we will take A, right? So we get this, and that equals what? That equals A inverse, right? So this gives us that A inverse is also in H. So what happens is that if we have A in H, any A in H, okay, I should have written this first. Then we already showed that E was in H, so we have, instead of this AB, we got EA. And as an implication, we saw A in H. That shows us that A inverse is also in H, right? And now we can show the closure, right? That if AB is in here, right, then what happens is that AB, okay, sorry about that. We showed that the inverse property is in there, right? So if B is in there, B inverse has to be in there as well, right? Okay. And if B inverse is in there, that means A combined with the inverse of B inverse. So that's how we are verifying it as an argument. So, and we have seen inverse of B inverse is B, right? That is AOB. And now that is going to be in H as well. Okay, let's just stick to the recording area, right? So this shows the closure. So what we did was we showed the associativity, identity, inverse, and closure in this order, but that's all right. So anyways, in order for uh, a non-empty subset to be a subgroup, all we need is this. Okay, if H is a non-empty subset of a group G and O is the operation, then this is enough to show that H is a subgroup. Okay, and this will come out pretty handy property. Okay, Now let's take up a case where the group that we have is a finite group, and let's let this have n elements. Okay. Later on, we will call this property as that the group has order n. But anyways, so we have a finite group G which has n elements, and we can then list the elements. All right. So say we list the elements as let's write identity separately and then index them like this A1 and now I went off the screen and just completed writing this. So it has n elements and I have listed them like this because you saw first I wrote E because E will be in the group, and the remaining n minus 1 elements, I wrote them like this. Now H, let's let H be a non-empty subset. And here you can see that if H is closed, okay, if H is closed, of course, under the operation that the group has, then we can see that that might be enough for H to be a subgroup. So let me just take it to our writing board. So now H is closed under the operation, and this is an associative operation because G is a group. So we have to show inverse and identity in H, right? Okay, so let's take any A in H, okay? And if A is E, then the job is done, right? Okay, it has identity and A is its own inverse. So for any A, I have the A inverse. Now let's say we have A different from identity. Then in that case, you can see if you take A is square, then that will be in H. Okay, so if that is not in identity, if this is not identity, you can again take A square times A, that will be in H. So what will happen? I mean, eventually you should get a power on A, say A U, that should become that should become the identity. All right, where U is what? Where U has to be between 1 and n minus 1, actually 2 and n minus 1, because we did this, we took A different from U. And then what you can do is we will have the identity just because of the closure, one time. Sometime it will go ahead and hit E, okay? Or, and then from this, you can split it as A times A to the U minus 1, and that will give you the inverse. So just to the formal writing of this, I'm leaving it for you as an exercise that if you have a finite group, then for a non-empty subset to be a subgroup, just closure under the operation is enough. Okay. Now let's just get a couple of things more. First of all, if I have any group G, if G is a group, then it will have identity, and identity alone that will satisfy all the properties for being a subgroup, right? And G itself is can be considered as a subgroup of itself. So given any group, there are always two subgroups, that is the identity, and G itself, they're subgroups of G, we call them improper subgroups. Okay. Now, let's see this here, that say we have, several subgroups. Let's take condition of 2, that we take H and K, they are subgroups of G. Okay. All right, we are given that these are subgroups and the operation is this. Let me erase this end because I think making a sketch will help. Okay, so give me a minute, I'll erase it and be right back. So now we have G, a group, right? And with say binary operation O, and H and K are subgroups. And we would like to see if H intersection K is a subgroup. Okay, so I'm just making a Venn diagram. Okay, so this is H, this is K, and they will have a non-empty intersection because identity is in both of them. Now, since G is a group, in order to show that H intersection K is a subgroup, all we need to show is that if A is in H intersection K, or rather AB is in AB are in H intersection K, then that should imply that this is AB inverse is in H intersection K as well. So AB are in H intersection K means AB, so are in H, right? And since H is a subgroup, AB inverse is in H. And again, AB are in H intersection K means they are in K, and so AB inverse is in K. So AB inverse is in both in H and K, so AB inverse H is in H intersection K. I think I would just formally write this one, won't take too long. So we are given that H and K are subgroups of a group G, and what we would like to show is that their intersection is a subgroup as well. So notice this, if A and B, they are two elements of HK, then AB, they, they belong to H, okay? At the same time, right, by the definition of the intersection, they belong to K as well, right? Now, what would this mean? That A, B inverse belongs to H. Why does it belong to H? Because H is a subgroup, right? Okay, so that belongs to H, and along the same lines, right? Along the same lines, AB inverse, because K is a subgroup and A and B are in K, that belongs to K as well, right? Okay, why does this happen? We can write it down, but I'm just supplying you just because of this property, right? That they're subgroups. And now what happens? Since it belongs to both of them, then AB inverse will belong to H intersection K, and that gives us a general verification that H intersection K is a subgroup of G. All right, so there's not really much writing. I don't know why I took so long. Okay, now again, let's say we have H and K. They are subgroups of a group G, okay, then, and say we have this situation, all right, that neither of them is contained in the other one, all right, and we want to investigate if H union K is going to be a subgroup or not, right? Okay, so because we just showed that the intersection is, and for union, we are going to look at that. Now, remember this, that we just had, if AB is in H union K, right? Then if we could show that AB inverse is in H union K, we are done. Now, if we take AB in H union K, then it may so happen, because as I said, we are taking the situation where H union K is neither H nor K, and E is a common element. So we have this kind of situation. So let's say A lives here and B lives here. All right. Now the question would be, it might so happen that AB may jump outside, right? Okay, so let's just go ahead and play with some examples and then see whether that is possible or not. All right. So the example that we are looking at, and I just went into scientific workplace, that let's take up the integers modulo 6, that is a group, and let's take these two as subgroups, and they are subgroups because look at their Cayley tables. Here you can see for H, all the outputs are in H. Same for K, all the outputs are in K. All right, so H and K are in subgroups. All right, are going to be subgroups. Now, remember this, all that we have to do is say take an element in, take two elements in H union K. All right, so three, and we would do this. We would try to, look at one element that is in H but not in K and vice versa. So here, 3 is the only element here. So how about this? We pick 3 and we pick 3 from here and 2 from here. So what we can see is this, that 3 and 2, they are in H union K. That will be this set here, 0, 2, 3, 4. But if we go ahead and say we add these two together, then what the sum will be? The sum will be 5. So, so we got 5, and you can see that 5 is not in H union K, right? So 5 is not in here. That means H union K is not closed, right? Under the binary operation. So let's just write this here, that 5 is not in or does not belong to. Okay, so 5 does not belong to H union K. All right, therefore let's write the whole thing, not rush. Okay, so therefore H union K is not closed under the under the binary operation, right? Not closed, okay, under this binary operation, and the binary operation is addition modulo 6, right? And is consequently is not a subgroup, right? Okay, is, sorry, consequently is not a subgroup of the group of, what did we take the symbol as, this integers modulo 6. All right, so here we go. So we saw that the intersection of two subgroups is a subgroup, but the union of two subgroups may not be a subgroup. I'm saying may not be a subgroup, okay? All right, you may get situations in which they are, and you'll get many. All right, so we are concluding this section here, and see you in the next presentation. All right.